What happens when light is incident on the surface of a transparent object? Consider a glass slab and suppose the narrow beam of light is incident on one side. The beam of light partially reflects, partially refracts, and it's even partially absorbed by the object. In the past, we have already discussed laws of reflection. Do you remember those laws? The first one says that the light ray which is incident is reflected in such a way that the angle of incidence and the angle of reflection are equal. And the second one says that the incident ray, the reflected ray, and the normal all lie in the same plane. Just like for reflection, there are some laws for refraction. And what is refraction? Refraction is the change in direction of light as it passes across the boundary separating two media caused by its change in speed. If the refractive medium is optically denser compared to incident medium, then the refracted ray will bend towards the normal. And if it's optically rarer, it will bend away from the normal. Note that the light is incident obliquely on the surface. When the incident light is perpendicular to the surface, it does not change its direction. There are two laws of refraction. Among them, the first one is same as the second law of reflection. Consider light travelling from some medium 1 to another medium 2, which is optically denser than medium 1. So its speed in medium 2 decreases and it bends towards the normal. The first law of refraction says that the incident ray, refracted ray, and the normal at the point of incidence all lie in the same plane. It means that if I were to draw this on a piece of paper, they all will be on the plane of paper and not out of the paper. What about the second law? The second law is also called Snell's law of refraction. Snell's law gives us the relation between the incident and refraction angles and the refractive indices of the mediums. What is the refractive index of a medium? It is the extent to which the refractive medium increases or decreases the speed of light. Mathematically, it is the ratio of the speed of light in the incident medium to the speed of light in the refractive medium. It's denoted by n, and the two numbers in the base are the two mediums. We read this as refractive index of medium 2 with respect to the incident medium 1. Also, V1 and V2 are speeds of light in medium 1 and 2 respectively. We can also define it as the extent to which light changes its direction in the refractive medium. Okay, let's discuss the Snell's law of refraction now. In simple words, it tells us that the ratio of the sine of the angle of incidence to the sine of the angle of refraction is equal to the refractive index of the second medium with respect to the first medium. Now look at the term on the right. It is constant for light of a given color and for the given pair of media. This is the basic idea of Snell's law, and there are different ways in which we can understand it. In the previous video, we'd seen what n/1 means. It is equal to the ratio of speed of light in the incident medium to the speed of light in the refractive medium. So we can also say that sine I over sine R is V1 over V2. There's yet another way to understand this. We may want to understand the ratio in terms of the absolute refractive indices of the medium. Absolute refractive index, if you remember, is the refractive index of a medium with respect to vacuum. For instance, if the refractive medium is water, then it's written like this. So can we find this ratio in terms of n1 and n2? Yes, we can. We just use some very basic math. We can write this ratio like this, where c is the speed of light in vacuum. Yes, if you simplify this ratio, we will get V1 over V2. And can you guess what the numerator and the denominator are equal to? That's right. This is nothing but the absolute refractive index of medium 2, and this is the absolute refractive index of medium 1. That was another way of understanding the Snell's law. We can also say that sine I over sine R is n2 over n1, where n2 and n1 are the absolute refractive indices of media 2 and 1 respectively. Hope you understood this well. Let's move on to a new page. So these were the two laws of refraction of light. In the next lesson, we will solve a simple example based on Snell's law.
Hi friends, are you ready to learn about colors of light, dispersion and spectrum in an exciting way? I have this light bulb here with me. It looks like a simple white bulb, but it's actually a magic bulb because I can change the color of this bulb using an app on my phone here. Let me show you how. So we have so many colors to choose from. For example, red light, pink, blue, green light, yellow. Wasn't that cool? Now I'm going to turn off all the lights in the room and we are going to use only this bulb. And we are going to look at these three blocks under different colors of light. Red light, green light and blue light. And let's see what these blocks look like under colored light. And as usual, we'll finish off with our top 3 questions on this topic. So are you ready for our exciting experiment? Lights off, please. I'm now going to turn on our magic bulb. First, as you can see, the bulb is giving off white light. We have 3 blocks here, red, green and blue. Now I'm going to change the color of the bulb to red. Wow! Can you see the red block here? But we can't recognize the color of the other 2 blocks. They appear blackish. This is in fact the green block and this is the blue block. Now why is this happening? Because there's only red light here. And the red block is able to reflect the red light so it's visible and appears red in color. But the green block absorbs all the red light and has no light to reflect, so it appears black. And same is the case with the blue block. It absorbs the red light and hence appears blackish in color. Now I'm going to change the color of the bulb to green. Under green light, can you see that the green block is visible, but the red block and the blue block appear blackish in color because the green block is reflecting all the green light, but the red block and the blue block absorb the green light, hence they appear blackish. Now I'm going to change the color of the bulb to blue. Now what do we have here under blue light? Can you see that the blue block is now visible, but the green and red block appear dark or black in color? Because the blue block is reflecting all of the blue light, but the green and red block are absorbing the blue light and hence they appear black in color. So what's our conclusion from the experiment? An object reflects light that matches the color of the object and it absorbs all other colors of light. Let's take an example. If we consider this red block here, it's reflecting red light. That's why it appears red to us, but it's absorbing all the other colors of light. Now when this red block was placed under different colored light, what did it look like? So under red color, it looked red in color. But when placed in blue and green light, it looked black because it was absorbing the green and blue light and it was not able to reflect any light because it can only reflect red light. That's why it appeared black. Similarly, the green block was visible under green light but appeared blackish under red and blue light. And same is the case for the blue block. So clearly we can see that these objects are reflecting light of their color, but they are absorbing all the other colors. When we look at these 3 blocks under white light, whether it's coming from this bulb or from the lights in this room, we can see all the 3 colors, red, green and blue. The red block is reflecting red light. The green block reflects green light and the blue block reflects blue light. So what does this tell us about white light? White light is actually not white. It at least contains these 3 colors, red, green and blue. But do you know how many colors there are actually in white light? That's right. The correct answer is white light contains millions and millions of colors. You may have heard of the 7 rainbow colors or the Viii colors, but that's just a simplification. White light is made up of millions and millions of colors. Now an interesting question is, Why does light have different colors? So what is the difference between red light, green light, or blue light? Let's compare light with sound. Light and sound are both energies. They are waves. So when I play music in this keyboard, why do these sounds sound different? What's the difference between these sounds? That's right. These different sounds have different frequency. Similarly, different colors of light are light waves having different frequency. So the frequency of red light is different from green light, and that's different from blue light. And all these light waves of different frequencies make up white light. Now, can we separate the colors of white light? Absolutely. Let's take a look how. When you shine white light on a glass prism, as you can see, the glass prism splits the white light into its constituent colors. And this splitting of white light into its constituent colors is called dispersion of light. And the band of colors obtained by this dispersion of light is called spectrum. As we discussed, the spectrum band contains millions and millions of colors. But here we've just shown the 7 rainbow colors, the Viii colors, violet, indigo, blue, green, yellow, orange and red, just for simplicity. But actually there are millions and millions of colors there. Now can you think of examples where you've seen a spectrum, where you've seen the dispersion of light? One simple example is the beautiful rainbow, where you see the white sunlight splitting into the different colors. And another everyday life example is, if you look at the back of a CD or DVD, have you seen the different colors? It looks almost like a rainbow. That's your spectrum, and it's happening due to dispersion of light. As we learnt, white light is made of 7 different colors: violet, indigo, blue, green, yellow, orange and red. This band of 7 colors is known as spectrum, and the splitting of white light into its constituent colors is known as dispersion of light. Now let's understand how our simple glass prism is able to split the white light into different colors. For this, we need the concept of refraction. Remember, refraction means bending of light. So let's start off by shining light of a single color, known as monochromatic light, let's say red light here, onto our glass prism. And as you can see, the light is traveling from air to glass, so there's a bending or refraction there. And once again there's a bending when light comes out of the prism, so from glass to air. And as you can see, the red light is bending towards the base of the prism here. Now let's replace the red light with white light. Again, for simplicity, we'll consider that white light is made up of the 7 Viii colors. Now one important point to remember is that different colors of light have the same speed in air, approximately 3 into 10 to the power 8 meter per second. So all our 7 colors are traveling at the same speed in air. But the moment they hit the glass prism, the speed of the different colors changes in the glass prism. Red has the maximum speed and violet has the minimum speed. So because of the change in speed of the different colors, they bend at different angles in the glass prism. So as you can see, they split there. And then there is another refraction when these different colors are coming out from the glass to the air. So this is how the glass prism is able to split the white light into its constituent colors. So the important point to remember is all the colors have the same speed in air. Otherwise, we'll be seeing a rainbow right here in the air. But in glass or in any other medium, different colors have different speeds, and that's how they split up. As we saw, our glass prism splits the white light into 7 different colors. Now what do you think is going to happen if we place a second prism but it's inverted after the first one? That's right, we are going to get back white light again. So these two prisms are showing that white light contains 7 colors. The first one is splitting the white light into 7 colors, and the second prism recombines the 7 different colors back to white light. Let's place the concepts we have learned so far on our concept board. Now let's talk about nature's beautiful spectrum, the rainbow. I'm sure you've seen a rainbow, but it's pretty rare, right? Because you need both rainfall and sunshine happening at the same time. And it only lasts a few seconds or a few minutes. But can you think of some places where you'll always see a natural rainbow? One thing that comes to my mind is near a waterfall. I've been to the Niagara Falls, and there you'll always see a rainbow. It never disappears, and people are clicking pictures around that rainbow. Let's discuss how a rainfall rainbow is formed. To see the rainbow, you need the sun behind you, and you need to be looking towards the rain. The raindrops are acting like tiny prisms, and they are splitting the white light of the sun into the 7 different colors, forming our rainbow. But it's not just dispersion of light involved, there's some other stuff going on. Let's take a closer look. Let's consider one raindrop for simplicity. When the white light from the sun enters the raindrop, just like the prism, it splits into 7 colors. Because light is entering from air to water in the raindrop. And we know that different colors of light will have different speeds in water. So there's dispersion there. Now, rather than all the colors of the light leaving the raindrop, an interesting thing happens which is known as total internal reflection of light. This takes place because light is traveling from a denser to a rarer medium, in this case from water to air. And the angle of incidence of light is greater than the critical angle of water. So instead of refracting, all the colors get reflected back. And now the 7 colors again try to leave the raindrop. This time the angle of incidence is lesser than the critical angle. So there is refraction of light. And that's how we see the 7 beautiful colors of the rainbow. As we've learnt, light is made up of many different colors. But if light wasn't so colorful, it would be like watching an old black and white movie. But we don't want that, right? So let's get the colors back on.